So, hello and welcome to EQUA's webinar about simulations on the cloud. I am now, can you hear us? Yes. We're still getting a lot of attendees here. The people are rapidly arriving. We're not up to the number we're expecting yet, so we will actually hold for a few minutes to allow people to join. Meanwhile, I will introduce myself and introduce Sven Mosberger, who's actually going to be the main attraction of this webinar. I will just be here to we're going to try a new version this time, and I will be here to bother him and ask perhaps the questions that no one of you dares to ask while he's doing it. My name is Per Salin. I'm the head of EQUA, and today we'll be looking at some really new, exciting things that we have been working on for a long time. It's primarily two things. One thing is the new IDA 5 release, which has a lot of new features. And we will actually not at all go through those features today. But we will, in a month or so, have another webinar where we go through the highlights of ICE 5, and we urge you to join this because there's a lot of goodies in there. The other good new interesting thing that we will be talking about today is to run ICE in the cloud. So all of the simulations that you'll be seeing today are done on a cloud server, and Sven is connected using a remote desktop to this cloud server, and this is a new form of delivery of ICE that we think is going to be very interesting for the future. There's two major advantages with running simulations or running ICE on the cloud. The really nice thing that we'll be focusing on today is the fact that we essentially have an infinite computational resource at our fingertips, and that's not something that we are usually used to having. Which means that you can actually literally start thousands of computers in a matter of minutes to run your cases. And just to give you a feeling, people might think that this is very, very expensive, and I don't have the exact figures here, but just to have an order of magnitude feeling for these costs, you know, if you have 1,000 servers working for you for 1 hour, that will cost approximately the same as you do for your client. So I mean, basically it's nothing compared to your own time that the actual computation cost. The other really nice thing about the cloud is that we can very easily avoid licensing, and for other types of software this is the main benefit for most people. So you can just sort of log in, pay as you go, and don't have to worry about licensing, and you can get the cost distributed to the project or person or company that you want it distributed to very easily. Today we will actually not talk so much about this cloud offering as a business proposition. You'll hopefully more see it in action to see what we can do with it. And the focus today for the technical demonstrations are these what we call parametric runs. So it's the class of simulations where you actually don't just do one simulation, but you change parameters automatically and generate large numbers of simulations. One key, and we have developed a common user interface for all these parametric runs that Sven will be showing you today. And the most simple type of simulation is the sort of what's usually called brute force, and that's that you run all combinations of all parameters. But if you have a very small number of parameters, this is possible. But as soon as you have bigger parameters and larger resolutions of what parameters you want to run, this becomes exorbitant. You can't do it. You have to do something else. One thing you can do then is to just run a few of those cases. That's usually called a Monte Carlo run. Sort of a statistical selection will show you that. Another one is a sensitivity run. You just change each parameter once essentially, and we'll show you that. The other type of parametric run that is usually discussed a lot is a proper optimization, where you actually try to minimize some cost function based on systematic parameter changes. This we will actually not show you today, there is such an optimization algorithm implemented, but we will not be talking so much about that today. We also have some work to do there. But for all of these various parametric runs, you need to make a lot of simulations in order to see something interesting, and this means that even on office type, hard sort of multiprocessor office hardware, this becomes very heavy. So that's why the cloud is so interesting. I will hand over to Sven, and he will start with just a very small example first to give you a show of these new features. It's a next to trivial example. And then after that we will show you a more interesting building, and that's where the main focus of the webinar will be. So welcome, Sven. I'll turn off the webcam now, and you can start showing your screen.
Thanks, Per, and good morning everybody from my side, and welcome to this webinar. Yeah, as Per said, I will now show a first case. So first of all, I'll explain what you see here. To the right, there's a normal web browser here. I opened the cloud service of IDA-ICE, and you simply can see here that I right now opened 2 IDA-ICE sessions, but I control these sessions remotely here from this remote desktop app where I can be on this virtual machine in the cloud. Okay, just have to avoid the Windows update right now. So here you can see this IDA-ICE. It looks actually exactly the same as it would look on a local machine. At least I did not find any difference here. So I can open a case and simply run this. And on this remote or on this session lock here, I can see what's happening. I can see the model that's running, and it's running an energy simulation, how long that's running. So it will run about 16 seconds, and then it will be terminated. So that's how it works here. Now I will explain the principles of parametric runs. So in this case I can go to Tools and Parametric Run, and here I can insert a new parametric run study, parametric run case. And in principle you can here define what parameter you want to vary, so the input parameter, and what result you want to look at for this parameter variation. So these are the outputs. You don't have to address these objects and parameters from here. I mean, you could do that, but that's complicated because you have to know how to code this, but you can do it in a much simpler way. So you can go to your model, open any form, and you can select the parameter. Here I take the supply air temperature. That parameter can either be in a form or in outline. You just right-click here and add this to your parametric run, and it will automatically be addressed to the right parameter. So my parameter is, yeah?
Just one little thing there. You can also do this in dialog boxes, but there the right-click menu is usually not available. Not every parameter is available in dialog boxes, but a lot of them, and then there will be some menu next to the parameter to do this with.
Ah, okay. Yes. Thanks. There is a basic value for this, so that's valid. That's actually valid, for instance, for a basic case in a sensitive analysis. We will see that later, or it's also relevant if you have a non-uniform distribution of the parameter. If you go to triangle, for instance, this value will be the most probable value for a statistics study like Monte Carlo simulation. But the parameter will be varied between those two ranges, so it makes sense to have this value within this range. So here in our case we will vary the supply air temperature from 8 to 32 degrees Celsius. We will do that with a brute force, and here we can select the number of cases that should be run. I select 15 here, and you will see later on, and these 15 cases running. But I also need to select the result, so I go to summary table and select the total delivered energy here. I can right-click on this table and add to parametric run here, and IDICE even recognizes this as a result and put it automatically to the output table. And actually here I go. I can run this brute force by clicking on Run All here. Just need to save the case before it will run. And this parametric study will open in my log, and the different cases, they are not yet open. They will open a bit later. So 15 cases will now be set up. You can see it here in the result table already, and they come up here as well in the log window. I can also define some reports here, put the input to the x-axis and output to the y-axis, for instance. And as soon as these calculations will be terminated, they will appear here both in the table, in the result table, and in the result diagram. And we can immediately see how total delivered energy varies with air supply temperature in this case. So they're coming up here.
Maybe, Sven, it's a good idea to point out that this kind of very small simulation is actually almost slower on the cloud server because there's an overhead for packing each case and so on. So the overhead becomes big for this kind of very small case.
Yeah. So yeah. That's true. Yeah, you actually realize that it took also longer than 16 seconds, but that's always the case. You can see here the total CPU time, which is on 5 minutes. So it did not take 5 minutes. That's how long it would take if you had to run it on one single core. So actually here the parametric run case, it went for 56 seconds, while every single case was 16 seconds. So you see here the overhead of packing these different cases. So, but you see here a clear optimum or minimum for the delivered energy. So that's a very simple case, and it's also simple to optimize. But in most real cases or practical cases, you would want to vary more than one parameter, or quite a large number of parameters, and also look at outputs at different outputs at the same time. So that's why we prepared here another case. Should be, no, let's close this one first. This one as well. So it's down here. So we have here now a small office house with totally 6 zones here. We have 2 meetings room to the left here, and we have 2 big office spaces here. We have a break room, and we have a reception hall. That's actually an atrium, and this atrium is only moderately cooled and heated. It's heated to 15 degrees and cooled to 30 degrees Celsius only. The whole building is mechanically ventilated with an air supply temperature of 18 degrees. So, but now I want to open this parametric runs. Before I do that, I will also show you how long it takes energy simulation here. So I just start this energy simulation. It will take a bit longer. So while running this case, I will show you the parametric run case of this. So you see that it started, and that's the reason why I have 2 sessions open. So I'll go to the other session now, which is actually the same case here, but the parametric run case is already open. At the tool you can see at the parametric run chapter here, you can see that actually you can also define more than 1 parametric run in the same model. We take this that is defined for the webinar here. And yeah, very often input parameters must be aggregated. For instance, you want to change the U value of an external wall with a single parameter. But in the model you have the conductivity of every layer of every wall type as a separate parameter. So you want to define 1 parameter that influences all the other parameters, and you can do that in different ways. One way is to use a resource, and I want to show you how you can do this. So in the 3D view, you can see at the south that we have some shading objects, and we also have this external shading, which is actually a horizontal simple screen here, and we want to vary the width of this simple screen, and for this we can go to the resource. So all these simple screens, they refer to 1 single resource called horizontal shading, and if you vary this parameter here in this resource, so you can go to 1 degrees for instance, so all these horizontal screen will actually disappear, and I can make them large again, and that means that I can vary now this resource parameter in my parametric run case, and it will come up here. I can rename that one to horizontal shading width, for instance, and let's vary this one from almost 0 to 30 degrees, like this. Another way of steering multiple parameters by just 1 is graphical scripting. And here we have another example. We have the glazing percentage in the north and the glazing percentage in the south. So actually right now the glazing percentage in the south is 75%, and we do have here a graphical script called window coordinate calculation. So we can define here these parameters, and if I change this for the south to maybe 30%, this graphical script will calculate all coordinates of these southern windows, and it will adapt immediately to the right percentage of glazing. So I also turn that back to 75%, which is actually my base case right now. So what more do I have? So these we also have the U value here, the thermal conductivity of all insulation layers in the building. But we also can use non-numerical parameters, so selections of objects, for instance. So it's an enumeration value actually, and we can also do that from resources, for instance. What we have here is a north atrium window, so it's the northern window of the atrium. I'll open that one, and I have here the control of its opening of this window. So, and I can use this control as a parameter in my parametric run, and you can see that you have 6 different selections for this, but I only want to use 2 of them, so I can select the 2 I want to use. One is a never open window, and the other one is a smart control of this window. And it is about these 2 windows here, the one here and the one here. So that's where I have the option to naturally ventilate my atrium. In the same way, I also use the glazing, so the selection of the glazing of north and south and of the atrium north and south. I also vary the glazing of all these windows. And then for the output, so I also present the output variables I want to look at. So one is actually a discomfort value, because it's the total person hours for person dissatisfied during a 1 year. So that's the PDH. It's coming from the summary table of the results, as the total delivered energy does. And I don't only want to see the total delivered energy, I want also see the split into cooling energy, heating energy, and lighting energy.
So Sven, maybe just to break the PDH is an IDA specific measure, and it's the integral of all PPDs essentially in the building. So it measures the total number of discomfort hours in a building. Yeah. Yeah. Sorry.
So yeah, exactly. So 1,000 means that during 1,000 hours 1 person is dissatisfied, or during 1 hour 1,000 persons are dissatisfied. That's how you can interpret this value. So as we vary the windows, also the window size and the window glazes, that's why we also want to now where something happened. So that's why I also want to run a daylight calculation, because I'm interested in daylight as well. So these 2 last parameters, they are daylight factors actually coming from the daylight calculation. So here, these are here from this result table. There is the median daylight factor of 2 zones here, an office space and a meeting. But that means that for the parametric run, for one parameter selection, I don't only want to start an energy simulation, but also a daylight simulation. So you can use multiple simulation for the parametric run. So each parameter settings needs to run two simulations, 2 different ones. And the last thing I'm interested in is a cost function. So we want to actually define one cost function, and therefore we can also use graphical scripting. So we have here a graphical script called cost function, and that's a very simple cost function, but it has three terms. One is a discomfort penalty. I have here again the PDH value we were discussing about, and 1 person hour or 1 hour of a dissatisfied person costs me 30 euros here in this cost function. And there is energy cost, where I have the delivered energy use of 1 year. I multiply this by kilowatt hour price and by 20 years. So I'm looking at the energy cost for 20 years of operation of this building. And then I have a term of investment cost here. So presently this one involves writing a traditional script, so I had to introduce here a script, but this will be simplified in the future. So actually, from the selection of glazing in my parametric run, it will then find a price of the glazing per square meter. And what's here right now missing is the total surface of external windows. We can find it here in the zone total. Where is it? More to the right, maybe. Now here is the total window surface, and I can add this to my cost function and can place it anywhere and multiply this price per square meter with the surface. And I have my total cost right now of 400,000 euros, and I can look at this cost function here. What I will now first do in my parametric run is run a sensitivity analysis. Before I do that, I check here my simulation time. It went up now to 11 minutes, which means that one energy simulation was about 5 or 6 minutes here, and I can now run a sensitivity analysis. I will explain what it will do then. Actually, I need to do that in my other window. That's where I just run this this energy simulation, and I will run here now my sensitivity analysis. So this parametric run opens immediately here, and we just wait for the sessions that will be open. I can then go to the result table here as well. So you can see here the basic values, which is 25 and 75, which is actually the first case. So it's this basic case of the sensitivity analysis, and then you can see that one by one parameter is varied. So first the glazing percentage in the north, and then it's the one in the south, and then it's the glazing in the north, glazing in the south, and the atrium glazings here, and then it goes down to the thermal conductivity that is varied, and all the other parameters, they are the same as in the base case. And then the horizontal shading is varied, and at the end also the atrium natural ventilation is turned off here. So in total it's 23, no, it's here, it's 21 sessions that are running, and I will now open a new kind of result presentation of such parametric run cases that we will implement. So here actually one case is represented, or one simulation is represented by one line. For instance, this is the basic case here. So we can see here what input parameter we selected. So it's 25% of north glazing in the north and 75 in the south. Then we have the selection of the different glazings here. We have the thermal conductivity, which is a value somewhere in between the two extremas. And then we have horizontal shading, and natural ventilation is turned on in the base case. And it's, yeah. So like this, we can, for instance, show at the variation of glazing percentage in the north. So here we have now 3 cases, and we can see that only the north glazing is varied. And we can see here the results. So to the right, you have the result parameters, and you can see that the glazing percentage in the north is not very sensitive to the delivered energy, the total one, but it's very sensitive to thermal comfort, and of course also to light comfort. And due to this, it's also sensitive due to both the investment function and the discomfort penalty. It's also very sensitive to our cost function. If we select, for instance, the glazing in the north, it is the other way around. So here actually you see that it's sensitive to delivered energy, but not very sensitive to comfort values. So yeah, and there is another one, that's the horizontal screen width, and here you see that the sensitivity is much lower. You can still see some differences, but here it is much lower. Yeah, so actually this is the sensitivity analysis, and we will now keep all the input values. We could decide to throw this simple screen with variation out of our future studies because it's not very sensitive, just to save some calculation time for the continuation of the optimization study. But we keep all these, and we want to run a Monte Carlo simulation as next. But for this, actually the running case was supposed to be finished, but it's not yet. Maybe you, Per, you can pre-pone something, or should I first explain the Monte Carlo study? So there is still...
Well, yeah, no, I think if we're waiting for this to that's another aspect of running on the cloud. There can be other people wanting the machines that you're using for right now. That will slow things down for everybody, of course. Normally, right now, this pool of machines that we're using is 100 machines. Normally, in production mode, it would be much bigger. So there can be some bottlenecks, probably ones that we have created here inadvertently. I could actually speak a little bit about, I expect that a lot of people are interested in release plans for these things. The IDE 5 that we've been working on for a long time, many years, will be the next major release of IDA, and we are almost finished with the beta version of this. So we're hoping to actually release a beta of ICE 5. It says early, I've written early fourth quarter, so that means October if things go as we want. It could even be a little bit before that if we're really lucky. So that's the timescale for the ICE beta, which means that it'll be in beta for at least some months before there's a formal commercial release. But we plan to make it available for interested users during this time. And just to finish off, although the simulations are almost done here, the release of the cloud platform will take another couple of months, but it's still not very far away. We will not initially offer anything else than ICE 5 on the cloud platform. We plan to be able to offer the ICE cloud platform with the ICE 5 beta towards the end of this year, basically. And then maybe in the future we'll add also 4.8 to this cloud platform, but that's not decided yet. It depends a bit on how long the ICE 5 beta takes. Okay, so how is it going, Sven?
Yeah, I think it's almost finished. So 38% of the cases are done, and then you can see here also the CPU time running faster than real time, of course. So we are on maybe 2.5 hours right now, and the cases are very soon finished. Actually, then the next step I will do is actually we already looked at the result of this sensitivity analysis. The next step I will do is run a Monte Carlo simulation here. As soon as this is done. I think it's not a good idea to start it before.
Yeah, but actually we're not going to do that now, but in principle, no, not on the same with the same session. But if you open, there's nothing in IDA 5. You can actually have multiple IDA sessions running at the same time, and you can and this block of computers, or this pool of computers that you have access to, this is just a queue of a lot of different jobs for every user on the IDICE cloud. So there's nothing stopping you from putting a lot of cases in this queue, and then if you or anybody else is already occupying the all of the allotted machines, so to speak, then it'll just take longer for you to get those cases delivered, so to speak. But you might also have seen that there's for runs, I mean, these runs take a matter of minutes here, but if you run things that take many hours, as I'm sure you often do, then you can actually get emails also, depending on to give you information about when your case is done. That's the notify me green button that you've seen there. It'll also be possible to get this web page that Sven has to the right there everywhere, including on an app on your phone, so you can wake up at night and check how your cases are doing.
Yes.
Okay,
so we are ready now to start the next simulation. I click on the button right now. So we will run 100 cases now, and what will be done right now, it will select randomly parameter settings in the range we defined, and with a probability distribution we defined. So we defined uniform there, so every parameter between these two range borders will have the same probability for these parameter selections. And before we click that, we can also select whether we want to keep the results or clear the results from previous runs. So this is now on yes, but we could also have selected no, in order to keep the sensitivity analysis runs together with the Monte Carlo run. So that can be done as well. And yeah, we will now just run 100 cases, so it means that this list here is even longer than before. So there are many cases, and I can also click the button that Per just mentioned, this notify when done. So I do that not on one of the cases, but on the parametric run case. So I will get an email as soon as this parametric run is finished. So let's go back to this one and open the results of the parametric run study, because this is now quite interesting.
So this is a bit television cook style. You have already done this before on the. So
exactly.
We're looking at the results of the simulation that you just launched.
Yeah. The simulation is not done, but the results are there.
Yeah, maybe I could just fill in now when the simulation is running, and we'll see. These distributions, now we've selected uniform distribution for everything, but it's very often so that you want to have skewed distributions. You have some typical value, and then you essentially want to have something looking a little bit like a normal distribution around that. Normal distributions are difficult to handle in practice because they need a lot of parameters and so on. So we are using triangular distributions that are weighted around the given the nominal value of the parameter. So you can have sort of a left skewed or right skewed or central or whatever skewness you want of a triangle distribution. Yeah. Go ahead, Sven.
Okay. Yeah, so we can see here immediately, for instance, with the lighting energy, there's just one case which is very high. Of course, we can always highlight one of the cases, which seem to be a bit tricky right now. Here it is, and you can immediately see that in this case you have almost no daylight, and that's due to very, very low glazing percentage on both sides, north and south. But a bit more interesting is if I, for instance, apply a color gradient here to the cost function. Just need to get rid of this highlight, and I can see that all these goal functions here I have, all these results, they correlate somehow to each other. This lighting energy is somehow inverted. I can also invert axis here in order to get this correlation. I can see it even nicer. But what I also can see that the input parameter that correlates most to all these functions, or at least to the cost function, is the glazing percentage here in both north and south. And that actually would mean that if I give a maximum to this PDH, for instance, no, probably to the cost function, the one with very high percentage will disappear here. So I can hide some cases here also to see what's going to happen.
Right. Maybe Sven, it's sorry to interrupt you, but maybe it's good to, not everybody might be familiar with this kind of parallel coordinates diagram. They look quite daunting in the beginning, but they're incredibly practical. So this color coding is an interesting way of distinguishing cases, but you can also sort of narrow the open window of cases that you want to look at that you just did, both for on the cost side and on the input side. So that's a very efficient way of sorting also.
Exactly.
Sorry. Yeah.
So I can apply this color gradient also for input parameter and look to what output it has an influence, and I can see that this atrium ventilation correlates most to the thermal comfort. So that means that if I give a maximum to the discomfort here, so I really want the comfortable example, I have to use the atrium natural ventilation. Otherwise, this one is my maximal comfort or minimal discomfort here. The same for daylight, for instance. There I want to maybe define a minimum here for these daylight functions, and then I will only have a few cases remaining here. And maybe I want the cheapest one of those three, or one of the two cheaper ones, and I am quite close, or I can now see what will be quite a good, I mean, there might be other combination of good parameters, of course, and it would be neat to have them all close together as here, because then I can be sure that the result is really good. But I can also show you what will happen when I now make some that's another thing I prepared when I narrow these ranges here, and I say the optimal solution should be always near these samples, for instance. So I can open a result of another session, which is actually the same results plus 100 more simulations here, and I can look at the same here. So I will even see more then. So I can again reduce my comfort here, also the daylight comfort I want to have in this range, and I can see that still thermal conductivity varies a lot, but I can also see that here some glazing here, for instance, if I colorize here, if I apply the color grading to this glazing here, I can really see that this low U value glazing is better than the double clear glazing. So I can clearly see here a difference mainly in energy consumption and thermal comfort. So I can turn off these, and then I colorize for this thermal conductivity, for instance. And here I can also see that this thermal conductivity, it is sensitive as expected to the total delivered energy here, of course. And again here I can then decide to use a low thermal conductivity, and you can see that now these two lines, at least, maybe it's by random, but these two lines, they are very close to each other, and I can be quite sure that this is close to an optimal solution. So I was able to do a simulation. Now you can also see the email that is coming, because this Monte Carlo simulation is finished. So I can do a manual optimization, or I mean it's not only automatic like I do it with a normal optimization case, but I can really decide between the different goal functions, between the different parameters I want to look at, and even discuss in a planning team how these different options behave and what advantages and disadvantages they have.
Maybe, Sven, we could stick in a little digression here of what we feel when working with this is very strongly that this is an interactive process. It's very seldom you formulate the optimal cost function that covers all of your goals and then just find the formal optimum or multiple, in a single or multi-objective sense of that cost function. but rather we think in practice it's very much a searching mechanism like you have illustrated here, where you make some rough low resolution runs first, and then you find a range of parameters that looks very interesting, and you can then keep the old examples that you have, but you add more examples in certain parameter ranges that you're more interested in. You can also extend the range of parameters of certain parameters. So we feel that the interactivity of this process of being able to change as you see the results come in, and also during while the results come in, is an incredibly important feature to make this practical. Right.
Yeah. So actually, Per, there was a question, I think, already. So Daniel just pointed out, so there was a question from the audience, and maybe this can start a question and answers, or do you want to point out something before this?
No, I think we're doing pretty well with time, and so I think we can open the Q&A session. Sure.
So Marzio Getzi asked whether IDICE 5 will be still be in 32 bits or whether it will be 64.
Right. So one of the issues we've had with ICE 4 is that we have had a lot of processes that need to share the 32-bit memory space, and this is one of the fundamental things that we have fixed in ICE 5. So there's still some 32-bit modules, but all of the key modules that use a lot of memory are 64-bit in ICE 5.
And maybe we can give instructions, so whenever someone wants to ask a question, it can either be done in the chat window, or you can raise hands also, and I think, and we can give you the microphone, and you can ask the question directly.
Right. So feel free to ask either chat or audio. Okay. So Sven, while people might be thinking about questions, is there anything else interesting you could show us?
Well, actually, I'm done.
You've done all of your examples.
Yeah. Mm-hmm. So I can do some yeah.
It's rare that these things go faster than expected, but that's fine. Yeah. We will be keeping time. We have another few minutes. Yeah.
Mm-hmm. So there's a question from Merda Drabani. Please, Merda Drabani, ask your question.
Hi. Thank you for your interesting presentation. Do you hear me?
Yes.
Yes, we hear.
My question was only about the graphical script that you implemented for the cost function, for the investment cost. Actually, I didn't understand that part. Is it possible to show it again? How did you for the Windows? I mean.
Okay.
Yes. Right. Yes, this part.
Yeah, so this is actually something we would change how it is. Right now this is a script, a manual script, so a script code that looks in the parametric run case and looks what glazing is selected, and then it gives a 1, 2, 3, 4. So it gives a numerical value instead of a name of a glazing. And this function here, it only defines if it's a 1, it's 1,800 euros per square meter. If it's a 2, it's 975, and so on. So this script gives a 1, 2, 3, 4, and this gives then the price. But in practice, later on, we will even add price parameters to our database, and hopefully almost all objects will then have a price, and then we can give function to that. Or maybe Per can tell.
Yeah,
more
maybe that's the dream scenario. Actually, it's very, very difficult to have meaningful prices in the database. We might do that at some point, but what we certainly will do is to provide slots for people in association with objects, where you can give, for example, a specific per area cost, or per perimeter cost, or per kilowatt cost, and so on, which is natural for that piece of equipment or building component. So this way of doing it that's done in the cost function now, this is only to show you that you know you can do this now if you want to, and the fact that this needed some coding was because the window type is an enumeration, and this requires some special functions.
Mm-hmm.
Right.
So did we answer?
We certainly see the point of now being able to make LCC calculations, and also actually involving life cycle analysis parameters. You know, looking at the total mass of certain parameters, certain materials in the building. So we think that. Now, given these new computational facilities we have, such simulations are actually both possible and interesting to do. Yeah.
Okay. We have a question from Frederick Mikkelsen. He asked, are you planning to implement better sensitivity analysis methods? So I'm not sure whether you're thinking at result presentation, because that's one thing we want to look at and have very good and nice result presentation methods. But maybe Per, you can say more about this.
Well, yeah, I mean this parallel coordinates tool that we are using or showing here, there are many such tools out there, and we will certainly be shipping one select and ship one of them, or make one easily available for you. But there's tons of innovative ways of presenting this data, and we will certainly be looking at that over time, hopefully in dialogue with users also, that can tip us off on good ways of presenting data, because this is not something we've had a lot of time to focus on so far.
Mm-hmm. So, and there is a question that we actually waited for, and it's how much would the cloud service cost?
Right, yes. Actually, I don't have those numbers in my head right now. We have, so I can't quote you exact euros on that. But I can tell you what our strategy for pricing is, and that we will be charging for a couple of different things on the cloud. One is actually eye-to-eyes modeling session time. So if you just have eye-to-eyes open on your screen and you're just looking at a model, for example, or making some lightweight simulations of that model, that the time that you have eye-to-eyes open will cost some money. And that cost we will try to get to be for a user to be neutral to an installed license cost. So it's not, you know, we're not intending the cloud to be any more expensive than an installed license in practice is, or a lot cheaper. So we want it to be relatively neutral, and that has led us to some per hour cost. I can't remember exactly what it is now. The other costs that you will have to pay for is obviously the renting computational servers cost, and I indicated the size of that earlier. So approximately, I mean, it's on the order of 10 US cents per core per hour, depending a lot on the machine you're running on and so on. but that sort of sums up to you know, on the order of 1,000 computers will cost about the same amount as you do per hour for your client. Then there are some other smaller costs that we are unfortunately have to charge for also, but they're not very burdening on your accounts. One is for storage, because we pay for the cloud storage, so you will pay also a little bit for the cloud storage. This is not a high cost, but it's to encourage you not to have enormous amounts of data stored in the cloud. Another thing I might add to that, perhaps, actually we're out of time here, but the other thing that I might add is that many people ask us if it'll be possible to send cloud cases or use the cloud computational resource from your local installation. And this is not something that we are not planning to offer at the moment. We'll see where the future brings us, because actually one of the costs in terms of both money and above all time is actually the time it takes to ship data from your local computer to and from your local computer to the cloud. Despite modern bandwidths, this is still a limiting factor, because you can imagine, you know, how much data a single ICE run can generate, and if you've done 1,000 of them, it'll be enormous amounts of data. So our philosophy is actually to operate the ICE on the cloud the way Sven has done now, and then also look at results on the cloud, and then only bring home the results and cases that you're actually interested in retaining. I mean, you can store it permanently on the cloud as well, but if you want to have them safely at home, so to speak, then you will be able to download those cases as well. Okay. So I think with that, our time is up. We can continue for a little bit longer if we have more questions. Otherwise, we will thank you for your attention. Do we have any more outstanding questions, or?
Yeah, there are many more questions, so we can go
so
on.
we will just tell people that thank you very much for joining, and if you have some other meeting to go to, please do, and then we will continue for some more minutes with the general discussion and questions here. Okay, yeah. So what's the next question then?
So maybe we can, because Ivan Plus had his idea was it's about the same topic as we just discussed. So he asked, is it possible to build our own ICE cloud server? So because they have a lot of free CPUs. So will this be possible?
It will not be possible initially. We will see again where time takes us. It's as I said, the actual computation cost is not the major part in this. Mm-hmm. So we're aiming to have as simple as possible target environment for this cloud edition of ICE.
Mm-hmm. So, and Jörg Kröger found very interesting the graphical scripting, and asked for tutorials or exercises probably. So I think I think there is no tutorial yet, but I also think that it's quite easy understandable, so you can see that just values are going in and they are multiplied and divided and summed up to any other goal function. But of course there are courses for this, and so you can go to the agenda and look for courses to learn more about this, and probably there is an online help as well.
Yeah, maybe I can fill in a little bit about our future plans on that. I lost almost all of your little speech now, but maybe that was just me. I hope not everybody else lost it. the graphical scripting you've seen it hasn't been invented by us, but it's adapted to us, because since IDA has had these types of connections between objects for a very long time, it's very intrinsic to the IDA design. We've decided to use the same objects basically for being able to make graphical scripts. So primarily now what's there at the moment is that we can look at primarily real numbers and progress them through various computational objects that most of you are already familiar with, that are primarily used for signals. So they are natural. It's natural to be able to do real number parameters also in the same way. One example of a non-real number was this enumeration for the selection of the glazing that we saw, and as you saw, we had to do a little fix for that with this script. In the future, of course, we could provide much more sophisticated graphical scripting possibilities where not just simple data types such as reals and enumerations can be used, but also much more complex data types, so that you can take entire objects and process them. We're not there yet, and we will see where the future takes us if this is something that becomes important to users. But we're certainly aware of this possibility. Anything else, Sven, in terms of questions?
Yeah, there are about 10 more questions, maybe slightly less. So Duarte Santos from Müller BBM asks, is there a limit to the number of machines one user can have access to during the parametric simulation?
There's no theoretical limit. There will be some practical limits. We need to have a subscription for a maximum pool of such machines, but this is all depending on the amount of, so we just want to not have to subscribe to a lot of machines that are never used. So we will extend this pool as people start to use this, and so if a lot of people use it, then we will certainly extend it quicker. There's no formal limit. It can be any number of machines basically. I mean, so there is, of course, yeah, but it's very, very large, yeah.
It might be that that one single user all of a sudden for one day wishes to use 100,000 cores or something like this. How this happen?
Actually, I'm not completely up to date on all the rules there. All I know is that the user will not be able to do that automatically without any questions asked, because that will obviously cost a lot of money. So we would want to there needs to be some filters there. There are some filters for EQUA as a company, but we will also have some filters for users, so that you don't do this by mistake, because you could run up huge bills very quickly by adding some orders of magnitude wrong numbers or something there. Yeah.
Okay. And Marcus Nisula asked, what is the state of the optimization module?
Right, yes, that's a question we absolutely expected. We've had plans and actually implemented the connection to a commercial optimization tool that we were planning to release. Unfortunately, the company that developed this was sold, and they changed their business policy, so this has disrupted our plans a little bit. So right now on the cloud, we're only offering GenOpt, the single objective optimizer, which is used a lot. I might add there that a tool like GenOpt is actually not benefiting very well from the cloud at all, because it uses parallelization to a relatively limited extent, and then it goes into sequential mode and tries to find the precise optimum in this sequential mode. And this last part is seldom interesting actually for building simulations. So we're actually looking for good good algorithms that use the parallelism all the way to the bitter end, so to speak, and so this is still a learning curve for us. But our feeling is that it'll be very nice to have some good multi-objective optimization tools, but in practice, this sort of study that Sven did now might very often be the more practical one to do. Yeah.
So, and there are two questions that are quite similar. Ferdinand 6 asks, is the parallel coordinate chart available for use now? If yes, how to get it for trying purpose? And Wolfgang Kampel asks whether we could show or explain how to export and import results from ICE to ICSTAT, and that actually gives the answers to Ferdinand 6. It's a tool called ICSTAT, and we did not implement it yet to ICE. We just plan to do that. So if you want to use this together with ICE 4.8, you can free download it. It's a simple JavaScript application, and you can simply import it from Excel. So there are some tricks you have to know. So you have to get rid of all spaces in the parameter names, and look that the number of digits is okay, and then you can just save it as a tab separated text file, and this text file then can be imported even together with a header to ICSTAT, and that's once you figure out how it works, it's okay. But there is some manual work which will disappear, of course, with ICE 5.
Any other questions?
So, and Anna Brown asks about ICE, whether it will also have the CFD tool, and will those results be possible to implement in the parametric run?
Yeah, that's a very good question. We haven't actually quite decided on that yet, but so it'll the release of the CFD is not coordinated with ICE 5, so ICE 5 will be released without the CFD is an add-in, or will be an add-in. It'll not happen with the ICE 5 release, but we plan to release a CFD beta also in the ICE 5 context very soon, and we should integrate also CFD into this optimization cycle for sure. Haven't done that yet though.
Mm-hmm. So we have a last question, at least for now. It's Wolfgang Schnell. He asked about the release plan, when the cloud version will be released, whether it will be along with 5 beta or later on separately.
The cloud, it'll be later on separately, but not very. So we plan to approximately release the beta hopefully in October now, whereas the cloud release we're targeting more late of the year, this year, for starting to use the cloud. The problem is that we can't release the cloud totally free of cost, because then it'll cost us a lot for people making a lot of stupid expensive experiments. So we will have to charge the users also initially on the cloud, and that requires a lot of things that must be safe and so on, and that's what we're working on right now. Okay, was that the last question or somewhere?
So that was the last question, yeah, no question left, maybe.
Right, so
no hands that rise, no,
okay.
no?
So I can see that we still have a quite large of number of attendees, so at least there's somebody for us to thank for their attention, and we will close the webinar now and turn to private conversations about these things instead. Thank you very much for your attendance and your questions.
Thanks from my side. Bye.